Hey everybody, welcome back to the Rule Your Pool podcast. I hope you've enjoyed the last few episodes. We've got some other very cool guests coming up, but this is episode 148, and I want to get back into what we normally do, which is pool chemistry and things that are relevant to those who are treating swimming pools for a living or those who own swimming pools. We are in the heat of summer. It is 2024. It has been very, very hot in North Carolina for sure, and many other places around the country. They're saying some record heat, and it brings up a question that we do get a lot. I've had this in my queue from requests from podcast listeners. By the way, if you have an episode request, that email, as you know, is podcast@orendatech.com. And that question is the relationship between temperature and sunlight and how long you can hold chlorine. There's a big difference between using chlorine and losing chlorine. And we've talked in previous episodes about what that difference is. So if you're struggling to hold chlorine for 7 days, pool pros listening, pay attention to this episode, because in this episode, I'm going to dive deeper, because I've done a lot of homework on this, into exactly what happens when sunlight gets into your pool. We're going to talk about solar UV radiation, the process of photolysis, or photodecomposition, or just destruction of chlorine, basically. And can you actually lose chlorine on a cloudy day? Does it have to be a bright, hot, sunny day? Let's get into it, episode 148.
Welcome to Rule Your Pool, the podcast by Orenda that explains and simplifies pool chemistry so that anybody, regardless of experience, can understand it. I'm your host, Eric Knight, bringing clarity to these subjects so that you can bring clarity to your water. If you're ready to rule your pool, then let's go.
Especially when the temperature is very warm, most people correctly recognize they struggle to hold chlorine for 7 days. So if that's you, listener, you are not alone. Most people struggle to hold chlorine for 7 days. It's hard. And I think this is one of those things that developed the habit over time of people putting tablets in their pool, trichlor, to get through those 7 days. Before getting further into this, as we discussed in a previous episode about chlorine labeled percentages, trichlor was never designed to be a primary chlorine. Now, it's used by many pool pros, successfully, by the way, maybe not for the most part, but successfully enough that it continues on. It has been used as a primary chlorine because, sure enough, after 7 days, you come back and there's a free chlorine reading. But over time, as we know, the cyanuric acid level climbs, and what really matters for disinfection is the free chlorine to cyanuric acid ratio. So if you have a very high CYA level and a very low level of chlorine, well, congratulations, you have chlorine, but is it effective? We know that CYA slows down chlorine, and there's a direct correlation between high cyanuric acid and problems like algae. Direct correlation, and cloudy water and other things like that. If chlorine is being truly effective, you should not have algae. And CYA is the first question we ask at Orenda. What is your cyanuric acid level? You might think, because we are Orenda, we make PR10000 phosphate remover, the first question should be, well, what are your phosphates? Nope. I can honestly tell you, we really don't ask that question. I mean, maybe way down the line if we're running out of other options, but typically, your phosphates are not the top priority when you're dealing with a green pool. They matter. They are an indirect relationship, but they're not the top priority. The top priority is, do you have effective sanitization? Do you have chlorine that is killing faster than whatever this contaminant is, in this case algae, can reproduce? Sanitizing is a race between the kill rate of the sanitizer and the growth and reproduction rate of the contaminant. If your algae is able to reproduce faster than your chlorine can kill it, you're going to have an outbreak. And if you can't hold chlorine for 7 days, well, you're probably going to have an issue, especially if it's really hot. So let's explore this relationship between hot, sunny days and not holding chlorine. I said it before the intro, and I've said it in so many episodes before. It's kind of catchy because it rhymes. There is a huge difference between using chlorine and losing chlorine. Using chlorine happens a lot faster in warmer temperatures. Why? More people are using the pool in the summertime. You got contamination of many different types, not just the people themselves and what's on them, things like sunscreen, lotions, cosmetics, things like that. So you're contributing to your chlorine demand in a big way right there. You also have natural contaminants getting in. You're mowing your lawn more, or you have people fertilizing more, and there's a lot more stuff that could potentially get into that pool. You have a lot more thunderstorms, typically, depending on where you are. I understand we're speaking to the world now. Amazingly, this podcast is international, which is phenomenal. But typically in the summertime, grass grows more than it would in the wintertime. You really get the most growth in the spring and the fall, at least where I live in the mid-Atlantic area. I'm in North Carolina. But you get my point. In the wintertime, you're not getting nearly as much contamination in that pool. The other thing is at a higher temperature, your chlorine is working faster. It's killing better. Most chemistry gets faster in warmer temperatures. The reactions themselves are happening better. Chlorine is performing better. And it's not just contaminants getting into the pool. What about contaminants that are already in the pool trying to reproduce? Like algae, germs, things like that. Those grow faster in warmer temperatures. It is no secret. This is why you don't really have to chlorinate in the wintertime if your water's below, say, 60 degrees Fahrenheit. You don't really have to. Your pool doesn't turn green in the winter, does it? Now, for those of you listening who are in an area that you're in a year-round market like Florida, Houston, Texas, Phoenix, Southern California, you still can, but it's not necessarily based on where you are. It's based on the water temperature and the air temperature. But I think you get the point. Chlorine is used up faster at higher temperatures. But there's a big misconception that says, well, because it's a higher temperature, I need more cyanuric acid because I'm unable to hold chlorine for 7 days. And the thought there, and it's incorrect, is that we're losing more chlorine in the summertime to sunlight. So we decided to put this to the test. I did a whole bunch of research for the past couple of weeks on this. I wanted to truly understand what is UV degradation of chlorine. We know that direct sunlight can destroy chlorine. There's no question about that. And there's a lot of studies on this. Some people call it photolysis of chlorine or just UV degradation in general. I use these terms interchangeably. Essentially what's happening is UV light breaks down hypochlorous acid and it becomes hydrochloric acid and oxygen. That reaction of chlorine being destroyed by sunlight has nothing to do with temperature. Now, reactions generally, like the use of chlorine, sanitization, oxidation, those happen faster at higher temperatures. So the chlorine gets used faster, which is what we want it to do, by the way. It's in there to be used. But it doesn't get lost to sunlight any faster, okay? So that was the first question. I wanted to really understand what is UV photolysis of chlorine? What is this degradation? How does that work? And then I had two questions from there. How does cyanuric acid slow it down or stop it? And does it stop it? And furthermore, what about cloudy days? I don't know about you, but I've been sunburned on cloudy days before, sometimes worse than the really sunny days. And it kind of sneaks up on you because you're not thinking about wearing sunscreen on a cloudy day. But sure enough, you come home and, man, I'm a lobster. Now, that probably has something to do with my complexion, but the point is this. UV light still goes through clouds, right? So let's discuss this. Let's first talk about the light spectrum. The sun emits a whole bunch of radiation, and we call this the electromagnetic spectrum. I'm going to throw a chart up here on YouTube. You can also find this in our blog. Just go on our blog and search UV, and you will see this. We're only showing what's relevant to swimming pools on here, by the way. There is a broader spectrum that includes things like X-rays, microwaves, radio waves, etc. All of this electromagnetic radiation comes from the sun, and it's across the entire spectrum. Now, the wavelength, meaning if you're looking at the wave, the distance between the apex of each wave is called the wavelength, and it's really, 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 really small, measured in, I believe, nanometers. So, for instance, a very short wavelength is a very intense ray of a lot of radiation, something like gamma rays, which can kill you. And as that wavelength lengthens out, it's able to penetrate things better, like clouds or glass or other things like that. The atmosphere, for instance. The longer the wavelength, the easier it travels. The shorter the wavelength, the more intense it is, but it doesn't have the ability to get through nearly as much. And thank God, because if our atmosphere and clouds couldn't stop gamma rays, we'd all be dead. There would be no life on this planet. But it can. And what we're talking about in swimming pools today has to do with specific wavelengths that impact chlorine. Now, in the blog, I've got it pulled up in front of me instead of show notes. Not that Jared would read them anyway. I've got a bunch of wavelengths on a graph that I created from a bunch of sources. The very low one is called, at least on this called extreme ultraviolet. And then you have UV, ultraviolet. Now, ultraviolet is not in the spectrum of light that we can see directly with our eyes, or at least not very well. And you start to be able to see it as it shows up to the light spectrum, which is between 400 nanometers and 700 nanometers. I know this sounds very technical, but if you see the graph, you'll understand. When you see the visible light spectrum, like you would see through a glass prism looking outside, it looks like a rainbow. It goes from purple on the left all the way to red on the right. And past red, meaning longer wavelength, so the light is spreading out, that electromagnetic wavelength is spreading out, it becomes something called infrared. We cannot see that with the naked eye. Infrared is invisible to us, just like UV is invisible to us. So the sun emits across this entire spectrum, from infrared to UV to extreme to gamma, all that stuff. The thing is, the shorter the wavelength, the easier it is to get blocked by things like the atmosphere, clouds, glass, things like that. The longer the wavelength, the easier it can go through. And by the way, in this same spectrum, you have things like X-rays, microwaves, and radio waves. Okay, all of these things have different wavelengths. According to different sources, one of them being the EPA and a few peer-reviewed articles, different wavelengths have optimum disinfection ability or the ability to destroy chlorine. So, for instance, according to the sources, optimal disinfection, if you've ever heard of a UV system used as secondary disinfection in an HVAC system or a swimming pool, is going to be about 264 nanometers of wavelength. That's right in the middle of UVC. You can see this on the chart. A residential UV system is going to be something called a low pressure UV system. It's usually going to be in a plastic housing because it doesn't get that hot, and it's going to produce light at this wavelength, and it's going to have great disinfection ability. When you get into the commercial pools, the venues, the universities, the YMCAs, the water parks, the swim schools, they're not usually using low pressure. They're using a more intense version of UV that has a broader spectrum of killing ability, and that's called medium pressure. So medium pressure can kill from 200 to 400 nanometers. Within that, you can destroy things like monochloramine, dichloramine, and even trichloramine if it's in the water. But trichloramine goes airborne. That causes the air quality issue. That's what got me sick and brought me into the industry. So if it's in the water, medium pressure UV can destroy these things. Low pressure UV can only destroy monochloramine and a little bit of chlorine. A little bit. A lot of manufacturers will say, no, it doesn't destroy chlorine. Well, it depends on the source you read, because some sources say it does, but it's never really noticeable. So I'm going to go and use Terry Arco's term, experientially. In the field, most people do not notice a loss of free chlorine using a low pressure UV system. They do notice a loss of free chlorine using a medium pressure UV system, even though it's somewhat minor. So it will reduce your free chlorine because of this UV degradation. Technically, what ultraviolet light does is it disrupts the DNA and the RNA of a pathogen so that it cannot reproduce. In other words, it inactivates it. It doesn't technically kill the cell. It just inactivates it so it can't grow again, and then that gives chlorine a lot more time to fully destroy it. That process is called protein unfolding. That's when HOCl smashes through the cell wall if it's a plant like algae, or through the cell membrane if it's a germ or bacteria or something like that, and it destroys the insides. That cell cannot reproduce. It is inactivated by UV. And that's a huge advantage. If we're talking about water quality, UV systems are great. So back to this, by the way, you can look at the chart. We'll throw it up on the YouTube channel here so you can take a look at it. According to most sources, chlorine is destroyed primarily by UVB rays. Now there's UVC, UVB, and UVA, depending on the wavelength. UVB rays around 295 nanometers. Now that's a little bit more than the optimal disinfection range, which is why low pressure doesn't really destroy free chlorine much. But there have been some studies that have used a low pressure UV system at 254 nanometers and found that it does destroy some chlorine, just not a lot of it. So that's the UV light spectrum. We know the sun is throwing all this radiation across the entire spectrum out. How much of it is getting to the Earth's surface? Thankfully, gamma rays are not. We'd all be dead. Infrared rays are, but we can't see them, and they're not destroying chlorine. So how much is getting there? Makes you wonder, right? What really matters, we found out from some studies, is something called fluence. Fluence is a fancy term for intensity. Now, the way that they measure fluence, and we talk about this in our blog, is they take, let's see here, I'm going to quote here, fluence refers to the total radiant energy passing through a small, transparent, imaginary spherical target containing the point of interest divided by the cross-sectional area of that target. It's basically measuring the intensity of that energy in one very small area. The sun is emitting all of this energy, but it's dispersed over, the entire universe. Because it's so diffused, its fluence is a lot less. The amount of energy that it throws out allows us to be surviving. Now think about it. We are millions and millions of miles away from the sun. I don't even know how many. I'm not an astronomer, but we're very far away, and you can feel the heat, right? Just imagine containing that and focusing that light. You can have a light bulb, and it throws off some light and can light up a room. But if you put it in a mirrored headlight in your car, you can focus that light and shoot that beam 100 feet ahead, and it's a much more intense beam because you've focused that energy and you've increased its fluence. That's the same concept here. So the question is, does the sun have enough fluence, enough intensity to destroy free chlorine? And the answer is obviously yes. We know this because the sun destroys chlorine. If you do not have cyanuric acid in your pool, your half-life, depending on the depth of the pool, is typically between 20 and 45 minutes. Now, there are some factors. Like I said, the depth of the pool is one of them because light refraction and all that. Another factor is clouds. Clouds don't stop UV. But what is a cloud? A cloud is full of moisture, and moisture at a molecular level is water. And that water refracts light and diffuses it, and it lowers the fluence of these UV rays coming through. They still get through, and they're enough to sunburn a guy like me. It's real. And they will still destroy some chlorine. They just don't destroy it as fast because they have less fluence. Then the question gets to, okay, if it can destroy chlorine, is there enough focused intensity for the sunlight to destroy things like chloramines? Generally, the answer is no. And we know this to be true because outdoor pools can have combined chlorine for a long time, and it doesn't seem to go anywhere. It would be very convenient in many ways if sunlight alone could destroy chloramines. For one thing, you would never have them in your pool. Every day that the sun rose, which is every day, it would be destroying chloramines, and that's just not happening. It does destroy hypochlorous acid, though. And that process, I'm going to read the formula here. When you put hypochlorous acid exposed to UV light in water, it will produce hydrochloric acid and oxygen. Technically, it's 2 HOCl's in UV light yields 2 hydrochloric acid and 1 oxygen. Now, I got that source from Bob Lowry's book, Used with Permission, and he's got a cool little graphic in there that shows how this works. That's basically the photolysis process. Sunlight separates it, and it creates hydrochloric acid and oxygen. Interesting. Acid. So the oxygen gets separated from the HOCl, and it leaves HCl. This may sound familiar to you if you are a regular listener of ours. Thank you, by the way. In episode 135, Terry Arco and I talked about chlorine's impact on pH. And we talked about how hypochlorite chlorines, like cal hypo and sodium hypo, meaning liquid chlorine, they only temporarily raise the pH of water. And the reason they only temporarily raise the pH of water is because when chlorine, HOCl, oxidizes, kills, or gets broken down in sunlight, that HOCl loses its oxygen and you get hydrochloric acid, and it brings the pH back down. That's what's happening here too. So as you lose chlorine to sunlight, your pH is actually going back down. Is it a lot? Maybe not. Depends on how much chlorine you have. So a lot of these things tie together. It's kind of cool. The deeper I go into this science, you start realizing, whoa, everything's tied together. The sun, the type of chlorine we're using, the amount of alkalinity, the amount of cyanuric acid, it's all a system. And one constant in all of this is that the sun rises every single day. Which brings me to my final point. We know that UV rays will penetrate through clouds. Now, UVC rays typically won't. They won't get through the atmosphere very well. Clouds for sure can block them too, but just the atmosphere alone can stop most UVC rays. But UVB and UVA rays, that's what sunburns us. UVB has more intensity. That does a lot more damage. UVA is the one that goes right through clouds. It can actually get through glass too as well. Glass will typically block UVC and UVB rays. So if you're inside your house, you're not going to get sunburned as much, but you can still get some sun damage from those UVA rays getting through. Yeah, pretty wild. By the way, as an aside, it's just coming to me now. If you have an indoor pool, like maybe you go to a health club or a YMCA or something like that, it's rare, but we do have customers call us with indoor algae problems. They almost always have either a low pressure UV system or they have windows that are not tinted. And those windows are either not double paned or they're not UV resistant enough. And those UVA rays can get through and it provides just enough sunlight for algae to reproduce with photosynthesis. Kind of crazy, right? You don't have indoor algae very often. Typically, it takes something introducing the spores because it's indoors. It's not like outdoors where spores are on every leaf and grass blade. But we've seen it. We've seen it quite a bit. And it's almost always from having big windows that are not blocking all of the UV entirely. But back to the final point. Cyanuric acid. We talk about it in probably 50% or more of our episodes. And that is because it is so important. It impacts just about every other aspect of pool chemistry. Certainly on indoor pools that don't use it, those lessons don't apply. But on any pool that involves stabilizer, we know things are fundamentally different, from the pH's impact on chlorine strength and efficiency. That fundamentally changes when you have CYA, because you can have a higher pH and have pretty much exact same strength of chlorine. You need to know the ratio of cyanuric acid to free chlorine, because what really matters is the amount of hypochlorous acid in the water. And that plummets to about 3% at just 30 parts per million CYA. Okay, so what we say in Pillar 4 is keep your cyanuric acid in a residential pool 50 or less, right? Just less than 50 is a good way of thinking about it. Just don't have too much. A little bit's really good. A lot of it becomes a problem. The more CYA you have, the more complicated your water chemistry comes. I also did an episode recently about cyanurate alkalinity, episode 143. CYA impacts that as well. So cyanuric acid, our old familiar friend, how does it actually work? Well, cyanuric acid binds to HOCl. It becomes something called a chlorinated isocyanurate, or a chloroisocyanurate. And I got to be honest with you, I could not find a definitive answer on if it's totally immune to sunlight or if it's just way more resistant to it. So if you know the answer to that, please shoot me an email. I want to learn this too. I couldn't find an answer. I was looking for it. But from what I understand, it's pretty much immune to sunlight degradation, maybe. Whatever it is, we know that chlorine will last much longer if it is stabilized. If it's not, as discussed a few minutes ago before I went on all these tangents, free chlorine, unstabilized, hypochlorous acid, and hypochlorite ion, their half-life is about 20 to 45 minutes. That's really fast. And within 2 to 3 hours, you're not going to have any chlorine anymore. Forget 7 days. You can't even get through half a day. Pretty crazy. But with stabilizer, you should be able to hold chlorine for a week, if you can manage how fast chlorine is being used. So again, we come back to this question of using chlorine versus losing chlorine. So let's recap all of this. The sun emits a lot of electromagnetic energy across the entire spectrum, from things that we cannot see, like gamma rays and X-rays and UV rays, and all the way on the other end of the spectrum, like radio waves and infrared. The light spectrum is somewhere in the middle that we can actually see. It's the UV rays that break down chlorine in a process called photolysis. The UV rays we cannot see with the naked eye can penetrate through clouds. Now, they do get diffused, and their intensity is reduced because the moisture in the clouds refracts that light and diffuses it. In other words, kind of dilutes it. And that decreases its intensity, and the technical word for that is called fluence. The fluence goes down Therefore, the rate of chlorine destruction can also go down. But make no mistake, on a cloudy, rainy, thunderstormy, overcast day, if that sun is up above those clouds, you can absolutely be losing chlorine in that pool. It may be slower, but it's still happening. I guess my main takeaway is this. If you have cyanuric acid, even a small amount of cyanuric acid stabilizer in your pool, the likelihood of you losing chlorine to sunlight is a lot lower than you think, at least not in a meaningful way. The chlorine demand, meaning using chlorine, goes way up when the temperature is hot and the sun is shining and all that stuff. It doesn't matter to CYA if it's a cloudy day or if it's a sunny day. Protection is protection. UV rays are going through those clouds too. You're going to have the same protection on a cloudy day that you do on a sunny day, but the use rate is much higher on a hotter day because more people are in the pool and more contaminants are getting into the pool. And the higher the temperature, the faster chlorine gets used up because the reactions are faster. So what can we do about this is we can supplement chlorine. Pillar number 2, if you've taken our 4 pillars, take variables out of your water. Give chlorine some support. I love the idea of using secondary systems. There's obviously UV, which we talked about. There's ozone, which is a phenomenal oxidizer and sanitizer. There's AOP, which produces hydroxyl radicals, a phenomenal oxidizer and sanitizer. And while these systems work in different ways, they can supplement chlorine. We make enzymes. You want to extend chlorine for a week? One of the best things you can do is use an enzyme. Doesn't have to be ours, but we make CV600, CV700. If you are trying to get your oxidant demand reduced, the vast majority of oxidants in a pool are going to be non-living organics. That's what enzymes break down and remove. You take those out of the equation, you've just reduced a huge burden on chlorine, and you got a fighting chance to hold it a lot longer. So take this information with you as you will. I hope this helps, and I hope this explains better why sunlight destroys chlorine. I'm Eric Knight with Orenda. This has been episode 148. Take care, everybody. Thanks.
Thank you for listening to Rule Your Pool, a podcast by Orenda Technologies. For more information on what we discussed in this week's episode, check the links in the description or visit www.orendatech.com.
I hope you find this show valuable enough that you tap that subscribe button and share it with your friends. You can also like us on Facebook and social media. And with our help, you'll be able to rule your pool without over-treating it with chemicals and wasting money. I'll see you next episode.